Assalamu alaikum class. My name is Nisharif and I'm from batch A. Today I'm going to present my assignment on boron nitride nanotube 3 type system, commonly abbreviated as BNNT-3. This presentation is a part of my MS chemistry course titled Material Chemistry, and it focuses on the structural, chemical and application based aspects of boron nitride nanotube with special emphasis on advanced boron nitride nanotube 3 type system. Nanomaterials play a critical role in modern science and technology, and among them, boron nitride nanotubes stand out due to their exceptional thermal stability, chemical inertness, and insulation properties. Throughout this presentation, I will explain about the history, introduction, crystal structure and morphology, physical and chemical properties of boron nitride nanotubes, their synthesis techniques, growth mechanism, functionalization, case study of palladium nanomaterial, their application, their linkage with SDGs and challenges, and at the end we will discuss about conclusion. Firstly, there is an abstract, but we will discuss about the abstract at the end of my presentation. Then there is history. Now I will start from history of boron nitride nanotubes. To understand the boron nitride nanotube 3, it is very important to first understand the historical background of boron nitride nanotubes. The concept of boron nitride nanotubes originated in the early 1990s following the discovery of carbon nanotubes. In 1994, theoretical studies conducted by scientists such as Marvin Cohen and his collaborators predicted that boron nitride, similar to graphite, could form stable tubular nanostructure. These calculations suggested that the hexagonal boron nitride sheets could roll into seamless cylinders, forming nanotubes with remarkable stability. In 1995, the theoretical prediction was confirmed experimentally. Researchers successfully synthesized the boron nitride nanotubes using the arc discharge method, which involved the generating a high temperature electric arc between boron containing electrodes in a nitrogen rich atmosphere. This experiment proved that the boron nitride could indeed exist in nanotube form. However, during the early years, boron nitride nanotube research progressed slowly due to low yield, poor crystallinity, short tube lengths, and high production cost. For many years, boron nitride nanotubes were produced only in milligram quantities and contained significant defects, limiting their practical use. Now there is improved high strength production. A major breakthrough occurred around 2009 to 2010 when advanced synthesis techniques such as high temperature pressurized vapor condenser method was developed. These methods enable the production of high crystalline, long and few-walled boron nitride nanotubes like boron nitride nanotube 3 in large quantities, paving the way for applied research. The boron nitride nanotube 3 type materials often referring to controlled multi-walled or functionalized boron nitride nanotube system emerged from this process. Now I will discuss the introduction of boron nitride nanotubes and explain why boron nitride nanotube 3 is important in modern material chemistry. Boron nitride nanotubes are one-dimensional nanomaterials composed of alternating boron and nitrogen atoms arranged in a hexagonal lattice and rolled into cylindrical shape. Structurally, they are very similar to carbon nanotubes, but chemically and electronically, they are quite different. One of the most important features of boron nitride nanotube 3 is their wide band gap, which is approximately 5.5 to 6 electron volt and remains almost constant regardless of tube diameter or chirality. This makes boron nitride nanotubes excellent and electrical insulator, unlike carbon nanotubes which can be metallic and semiconductor. Boron nitride nanotube 3 is not a universally fixed term but is commonly used in research to describe specific boron nitride nanotube systems such as few-walled boron nitride nanotubes, multi-walled boron nitride nanotubes, and functionalized boron nitride nanotube batches designed for advanced applications. These materials represent the transitions of boron nitride nanotubes from simple nanostructure to engineered hybrid system used in catalysis, environmental remediation, and high-performance composites. Let us now discuss the crystal structure of boron nitride nanotubes. Boron nitride nanotubes are derived from their hexagonal boron nitride, where boron and nitrogen atoms are arranged in honeycomb lattice similar to graphene. Each boron atom is covalently bonded to three nitrogen atoms through strong sp2 hybridized bonds. However, due to difference in electronegativity between boron and nitrogen, the boron and nitrogen bond has a polar end polarity and a partially ionic character. When hexagonal boron nitrogen sheet is rolled into tube, it forms a seamless cylindrical structure known as boron nitride nanotube. The boron nitride nanotubes can exhibit different chiralities such as zigzag and chiral configuration, but unlike carbon nanotubes, their electronic properties do not strongly depend upon chirality. This chirality independent behavior is a key advantage of boron nitride nanotubes. The polar nature of boron and nitrogen bond provides the high chemical stability, resistance to oxidation, and excellent performance in harsh environment, including high temperature and corrosive conditions. Single-walled and multi-walled BNNT-3. Based on their morphology, BNNTs can be classified into single-walled and multi-walled structures. Single-walled boron nitride nanotube consists of single atomic layer forming the tube. These nanotubes have a very high surface to volume ratio, making them ideal for surface functionalization and interaction with other materials. Multi-walled boron nitride nanotubes, on the other hand, consist of multiple concentric boron nitride layers separated by van der Waals forces. These structures exhibit great mechanical strength, high thermostability, and improved structure integrity. Multi-walled boron nitride nanotubes are generally easier to synthesize at larger scales and are commonly used in composite materials. Now, their next heading about physical and chemical properties of boron nitride nanotube. Boron nitride nanotubes exhibit exceptional mechanical strength, making them one of the strongest known one-dimensional nanomaterial. Their Young's modulus and tensile strength are comparable to, and in some cases even exceed, those of carbon nanotubes. This remarkable strength originates from the strong covalent bonding between boron and nitrogen atoms, where each atom is linked through robust sp2 hybridized bond forming a stable hexagonal network. An important advantage of boron nitride nanotube 3 over carbon nanotubes is their ability to retain mechanical integrity at elevated temperatures. While carbon nanotubes begin to degrade or oxidize at relatively low temperature, boron nitride nanotube 3 maintain their stiffness and resistance to fracture even under extreme thermal conditions. Their thermomechanical stability makes them particularly suitable for high temperature structure application. Due to these properties, boron nitride nanotube 3 are widely studied as reinforcement agents in polymer, ceramics, and metal matrix composites. When incorporated into composite material, boron nitride nanotubes significantly improve strength, toughness, and durability without adding excessive weight. This makes them especially attractive for aerospace, defense, automotive, and other applications. Their next property is thermostability and conductivity. One of the most distinguishing and valuable features of boron nitride nanotubes is their outstanding thermal stability. Boron nitride nanotube 3 can remain structurally stable in air at temperature up to approximately 900 degrees Celsius, which is significantly higher than oxidation limit of carbon nanotube. This high oxidation resistance is attributed to strong boron nitride bond and the chemical inert nature of boron nitride. In addition to thermal stability, boron nitride nanotube exhibit a high thermal conductivity along the axial direction of the nanotube. This means that the heat can be efficiently transported along the length of nanotube, making boron nitride nanotube 3 effective heat dissipation material. At the same time, their electrical insulation properties allow thermal management without electrical interference. The combination of high thermal conductivity and excellent oxidation resistance makes boron nitride nanotube 3 material highly promising for thermal management system in electronics, high power devices, aerospace components, and environment exposed to extreme temperature. These characteristics position of boron nitride nanotubes are ideal candidates for next generation heat resistant nanomaterials. This figure typically includes the microscopic and spectroscopic analysis such as TEM, SEM, XRD, FTIR, or Raman spectroscopy, which together confirm the successful synthesis of boron nitride nanotube 3 material. From the microscopic image, we can observe the tubular morphology of boron nitride nanotube 3, clearly showing the long cylindrical nanotube structure with uniform diameter. The presence of multi-walled concentric layers indicates that boron nitride nanotube 3 consists of few-walled or multi-walled boron nitride nanotube. The smooth tube walls and consistent interlayer spacing demonstrate high crystallinity and low defect density. High resolution TEM images reveal well ordered hexagonal boron nitride lattice fringes, confirming the formation of sp2 bonded boron nitrogen networks. This ordered atomic arrangement is responsible for excellent mechanical strength and thermal stability of boron nitride nanotube 3. Overall, this figure confirms that boron nitride nanotube have clearly crystalline structure, controlled morphology, and purity suitable for advanced application. Next heading there is electrical and dielectric properties. Boron nitride nanotube possesses a wide electronic band gap of approximately 5.5 to 6 electron volts, which classifies them as excellent electrical insulator, unlike carbon nanotubes whose electronic behavior can vary between metallic and semiconducting depending upon chirality. Boron nitride nanotube consistently exhibit insulating or wide bandgap semiconductor behavior. This chirality independent electronic nature is a major advantage as it ensures uniform and predictable electrical properties across different boron nitride nanotube samples. The wide band gap arises from the polar nature of boron and nitrogen bond, which creates strong localization of electron and suppresses electrical conduction. As a result, boron nitride nanotube 3 system are highly suitable for use as dielectric fillers, insulating coating, and electrical insulating components in nanoelectronic and microelectronic devices. They are particularly valuable in application where electrical isolation must be maintained alongside the thermal conductivity and mechanical strength. Now I will discuss the main synthesis techniques used to produce boron nitride nanotube, focusing on their principal advantages and limitations. The first method is induction thermoplasma synthesis. Induction thermoplasma synthesis is an advanced high-energy technique used for the large-scale production of boron nitride nanotube 3 with exceptional purity, crystallinity, and structure uniformity. In this method, high-frequency electromagnetic field ionizes nitrogen gas to generate stable plasma flame with temperature exceeding 12,000 K. Fine boron powder or boron coating precursors are injected into plasma zone where they instantly vaporize into atomic species. The activated boron react rapidly with dissociated nitrogen radical in the gas phase to perform boron nitride molecular cluster. As these clusters undergo rapid quenching in a controlled cooling region, they self-assemble into tubular nanostructure rather than bulk particles, resulting in a highly crystalline and low-defect boron nitride nanotube 3. This technique enables continuous scalable production with minimal contamination, making boron nitride nanotubes suitable for demanding applications such as aerospace, composites, radiation shielding, and high-temperature thermal management systems. Their next method is template assisted nanochannel growth. In this method, we will also discuss about the production of boron nitride nanotube, how they produce. It is very precision controlled synthesis technique used to fabricate boron nitride nanotube 3 with highly uniform dimensions, their excellent alignment, and how their defect can be reduced. In this method, non-porous templates such as anodic aluminum oxide or silica membranes containing well-defined nanochannels act as physical mold that guide nanotube formation. Boron containing precursor material are infiltrated into these nanochannels using coverage. Their field template is then subjected into high temperature heat treatment in a nitrogen or ammonia atmosphere, where the precursors undergo chemical conversion and crystallization into boron nitride along the inner walls of nanochannels, forming hollow nanotube structures. Their confined geometry of template enforces precise control over nanotube diameter, wall thickness, and alignment, minimizing random growth and structural defects. After synthesis, the template is selectively dissolved using chemical etching, releasing ordered arrays of high purity boron nitride nanotube 3. This method offers excellent reproducibility and dimensional accuracy, making it ideal for applications requiring controlled architecture such as nanoelectronic sensors and high performance composite reinforcement. Next, their third method is molten salt assisted synthesis. In this method, we will also discuss about the production of boron nitride nanotube 3 type system. It is an efficient and scalable technique to produce boron nitride nanotube with their controlled morphology, smooth surface quality, and improved crystallinity at relatively lower temperatures. In this method, boron precursors and nitrogen sources are mixed with alkali molten salts such as sodium chloride or potassium chloride, which act as liquid reaction medium and promote enhanced mass transport and uniform heat distribution. Upon heating above the melting point of salt, reactants dissolve partially and form high reactive species that facilitate the nucleation and growth of boron nitride nanotubes. Thus, the ionic environment of molten salt stabilize the tubular crystal formation and suppress unwanted particle agglomeration, resulting in uniform diameter and well-defined wall structures. Thus, controlling cooling further improves crystallinity and structural integrity. After completion of the reaction, salt is easily removed from water by washing or mild chemical treatment, leaving behind the pure boron nitride nanotube 3. This method also offers a scalability, lower temperature consumption, and cost efficiency, making it suitable for bulk manufacturing of boron nitride nanotube 3 for advanced composite material, thermal management system, and industrial application. To further understand boron nitride nanotube 3 formation, it is essential to explain the growth mechanism responsible for nanotube development. We will discuss about the growth mechanism. The first mechanism is root growth. In root growth mechanism, catalyst nanoparticles remain anchored to the substrate surface during the nanotube growth. Boron and nitrogen containing species diffuse into catalyst particle at high temperature. Once the catalyst becomes supersaturated, boron nitride precipitate at the catalyst substrate interface, initiating nanotube formation. As growth continues, the nanotube elongates away from the catalyst, while catalyst remains fixed at the base. This mechanism often leads to aligned or vertically oriented boron nitride nanotube array, and the nanotube diameter is largely determined by the catalyst particle size. Second mechanism is vapor liquid solid model. The vapor liquid solid growth mechanism is a widely accepted model for explaining the formation of boron nitride nanotube during chemical vapor deposition and other catalytic synthesis process. The vapor liquid solid mechanism is widely used at high temperatures. Boron and nitrogen containing species from the vapor phase dissolve into these droplets until supersaturation occurs. Once the saturation Once saturation is reached, boron nitride precipitates at the liquid solid interface, forming a nanotube that grows axially as more material is supplied. The catalyst droplet size determines the nanotube diameter, while growth temperature and precursor concentration control crystallinity and growth rate. After discussing the synthesis and growth mechanism of boron nitride nanotube, the next important topic is functionalization. Functionalization is essential because boron nitride nanotube 3 are chemically inert and difficult to disperse, which limits their practical application. Functionalization of boron nitride nanotube refer to intentional modification of nanotube surface in order to improve their compatibility, dispersibility, and interaction with other materials. Through functionalization, boron nitride nanotube 3 can be transformed from inert nanostructures into highly active and application-specific nanomaterials, particularly in composite, catalyst, and environmental remediation. The first functionalization is covalent functionalization. Covalent functionalization involves the formation of strong chemical bonds between functional group and surface atoms of boron nitride nanotube 3. In this approach, the chemical reactions are used to attach functional groups such as hydroxyl, amine, and carboxyl onto the boron and nitrogen atom present on the nanotube surface. This type of functionalization significantly improves the solubility and dispersibility of boron nitride nanotube in aqueous and organic solvents, as well as their compatibility with polymer matrix. As a result, functionalized boron nitride nanotube can be uniformly distributed within composite materials, avoiding agglomeration. Another major advantage of covalent functionalization is enhancement of interfacial bonding between boron nitride nanotubes and their surrounding matrix. Strong interfacial adhesion improve load transfer efficiency, leading to superior mechanical performance in composite system. This is especially beneficial for structural application where strength, stiffness, and durability are critical. However, it is important to note that excessive covalent modification may slightly alter intrinsic structure of boron nitride nanotube 3, so reaction condition must be carefully controlled. The second functionalization is non-covalent. Recent research has focused on non-covalent functionalization is based on weak physical interactions such as pi-pi, stacking, hydrogen bonding, and electrostatic forces rather than chemical bond formation. In this approach, molecules such as polymers, surfactants, and biomolecules are absorbed onto the surface of boron nitride nanotube without disturbing their underlying crystal structure. One of the most important advantages of non-covalent functionalization is that it preserves the intrinsic mechanical, thermal, and electrical properties of boron nitride nanotube. Since no covalent bonds are broken or formed within nanotube lattice, the original strength and thermostability remains intact. This method greatly enhances the dispersion stability of boron nitride nanotubes in both aqueous and organic solvents. Improved dispersion leads to more uniform nanocomposites with enhanced performance. Nanocovalent functionalization is particularly useful in applications where maintaining boron nitride nanotube integrity is critical, such as flexible electronics, biomedical system, and polymer nanocomposites. The third functionalization is metal decorated boron nitride nanotube 3. This method focused extensively on metal decorated boron nitride nanotube, where metal nanoparticles such as palladium, platinum, or silver are deposited onto boron nitride nanotube surface. These systems are often referred to boron nitride nanotube 3 type materials, indicating specifically engineered and functionalized boron nitride nanotube designed for advanced application. In these hybrid systems, the boron nitride nanotube act as a stable support, while metal nanoparticles provide the active catalytic or sensing sites. The strong interaction between the metal nanoparticles and the boron nitride nanotube substrate prevents nanoparticle agglomeration and enhances stability. Metal decorated boron nitride nanotube 3 system exhibit synergistic effect where the combined properties of boron nitride nanotubes and metal result in superior catalytic, photocatalytic, and sensing performance. These materials are particularly promising for environmental remediation, energy conservation, and advanced nanotechnological application. Now I will discuss a specific and important example of boron nitride nanotube 3 functionalization, which is the palladium boron nitride nanotube 3 hybrid nanomaterial. Firstly, we will discuss about the structure and synthesis of palladium boron nitride nanotube 3 hybrid. Palladium boron nitride nanotube 3 hybrid nanomaterial consists of palladium nanoparticles uniformly deposited on surface of boron nitride nanotubes. In this system, boron nitride nanotube 3 refers to a specifically synthesized boron nitride nanotube material with controlled morphology, high purity, and enhanced surface area, making it an excellent spot for metal nanoparticles. The synthesis of palladium boron nitride nanotube 3 hybrid is typically achieved using chemical reduction or impregation method. Palladium precursor salt are introduced into boron nitride nanotube suspension and subsequently reduced using suitable reducing agent. This process results in a C2 formation of palladium nanoparticle that strongly adhere to boron nitride nanotube 3 surface. Strong metal spot interaction prevent nanoparticle aggregation and ensure uniform dispersion, which is essential for achieving high catalytic efficiency. Second is the role of boron nitride nanotube, which act as a catalytic spot. Boron nitride nanotube 3 system serves as an ideal catalytic spot due to its high surface area, tubular morphology, chemical inertness, and excellent thermal stability. The hollow nanotubular structure provides abundant absorption site for organic pollutants, allowing contaminants to accumulate near the palladium active site. This absorption capability enhances the reactant catalyst interaction, leading to improved reaction kinetic and high catalytic efficiency. Additionally, the robust structure of boron nitride nanotube 3 ensured that hybrid system maintains structural integrity even under harsh photocatalytic conditions such as prolonged light irradiation and oxidative environment. Third is the photocatalytic mechanism and charge transfer. Under light irradiation, palladium, which deposits on boron nitride nanotube hybrid, exhibits superior photocatalytic performance due to efficient charge separation and transfer mechanism. Palladium nanoparticles act as electron trap, capturing photo-generated electrons and suppressing electron-hole recombination. This charge separation prolongs the lifetime of charge carrier and promotes the formation of reactive oxygen species such as hydroxyl radicals and superoxide radicals. These species possess strong oxidative potential and play a key role in breaking down complex organic pollutants. The fourth subheading is photocatalytic performance in pollutant degradation. Experimental studies have demonstrated that palladium which is deposited on boron nitride nanotube 3 hybrid achieve exceptionally high photocatalytic degradation efficiencies, often exceeding 95% for pollutants such as synthetic dyes and pharmaceutical residues. The high degradation rates indicate not only rapid pollutant removal but also near complete mineralization into environmentally begun products such as carbon dioxide and water. This confirms the effectiveness of boron nitride nanotube 3 based hybrid system in environmental remediation. Next, fifth subheading is how they are stable, reuse, and environmentally significant. Beyond the high activity palladium, which is deposited on boron nitride nanotube 3 hybrid nanomaterials, exhibit excellent stability and recyclability. In addition to the high activity, boron nitride nanotube hybrid exhibit excellent stability and reusability. Multiple photocatalytic cycles show minimal performance loss, indicating strong anchoring of palladium nanoparticles and resistant to metal leaching. Their durability makes palladium which is deposited on boron nitride nanotube 3, highly suitable for long-term wastewater treatment application and sustainable photocatalytic technologies. The case study early demonstrated how boron nitride nanotube functionalization significantly expand the application potential of boron nitride nanotube. Finally, I will discuss the major application areas of boron nitride nanotube 3 material. First is structure and aerospace application. Boron nitride nanotubes are extensively used as reinforcement agents in lightweight composite materials due to their exceptional strength to weight ratio. The strong boron nitrogen bonding provides high tensile strength and stiffness, enabling effective load transfer of polymer, ceramic, and metal matrix. Their excellent thermal stability and oxidation resistance allow boron nitride nanotube reinforced composites to maintain performance at elevated temperatures, making them ideal for aerospace and defense applications where materials are exposed to extreme thermal and mechanical stresses. The second application is energy and environmental. In energy and environmental sectors, boron nitride nanotube 3 are used in filtration membranes, water purification systems, and hydrogen storage technologies. Their hollow tubular structure, high surface area, and chemical inertness enhance filtration efficiency and durability. Boron nitride nanotube 3 hybrid systems, especially metal decorated variants, show significantly enhanced photocatalytic performance, making them suitable for pollutant degradation and environmental remediation. Next, their application is biomedical. In biomedical field, the enhanced photocatalytic performance of boron nitride nanotube 3 hybrid system arises from efficient charge separation and reactive oxygen species generation. These reactive species interact with organic contaminants, breaking chemical bonds and converting them into harmless products. Additionally, the high surface area and tubular morphology of boron nitride nanotube 3 facilitate absorption and interaction with biological molecules, opening pathways for biomedical imaging during delivery, and antibacterial application provided biocompatibility is carefully controlled. Then now I will explain how functionalized boron nitride nanotube, especially boron nitride nanotube 3 system, connect with the United Nations Sustainable Development Goals. This is very important perspective as it demonstrates how advanced nanomaterials contribute to global sustainability, energy efficiency, healthcare, and industrial innovation. Functionalized boron nitride nanotube 3 nanomaterials exhibit exceptional thermal stability, chemical inertness, and mechanical strength, and tunable surface properties, making them highly relevant to sustainable development. These properties allow boron nitride nanotube 3 to contribute the several SDGs, particularly in healthcare, clean energy, industry, urban development, responsible production, and climate action. There is SDG 3, good health and well-being. Boron BNNT-3 show excellent biocompatibility and low cytotoxicity compared to many carbon-based nanomaterials. Functionalized boron nitride nanotubes are currently explored for drug delivery system, biomedical implants, biosensors, and radiation shielding in medical environments. Their ability to enhance targeted therapy while reducing side effects contributes to safer or more effective healthcare technologies, directly supporting SDG 3. Next is SDG 7, affordable and clean energy. BNNT-3 plays a crucial role in clean energy application due to its high thermal conductivity, electrical insulation, and resistance to extreme conditions. BNNT-3 based nanocomposites are suitable for energy storage system, hydrogen storage, nuclear reactor insulation, and thermal management in renewable energy devices. These applications promote energy efficiency, reduce energy losses, and support the development of sustainable energy solutions. Now there is SDG 9, which is about industry, innovation, and infrastructure. BNNT-3 contributes to SDG 9 by enabling advanced industrial materials with superior mechanical strength, lightweight properties, and durability. Functionalized boron nitride nanotube enhance the performance of aerospace, automotive, electronics, and defense materials, supporting innovation, resilient infrastructure, and sustainable industrial development. SDG 11, which is about sustainable cities and communities. Integration of boron nitride nanotube 3 into construction and protective material improve fire resistance, thermal insulation, and structural durability. These properties support the development of safer building, improve the protective coatings, and smart material for urban development, helping create resilient and sustainable cities. Next, there is responsible consumption production, which is covered in SDG 12. Functionalization of boron nitride nanotube 3 promotes material efficiency and longer productive lifetimes, which reduce material waste and the need of frequent replacement. In addition, research is focusing on eco-friendly synthesis and safer surface modification, ensuring the boron nitride nanotube 3 development aligns with the sustainable manufacturing and responsible use of resources. At the end, there is climate action, which is under SDG 13. BNNT-3 contributes indirectly to climate action by enhancing energy efficiency, enabling lightweight materials, and improving thermal management. Its role in renewable energy technologies and advanced insulation systems help reduce greenhouse gas emissions, supporting global efforts to mitigate climate change. Despite the remarkable properties of boron nitride nanotube 3, there are still several challenges that researchers need to address to enable widespread practical application. Means we will discuss about the challenges and future prospects of BNNT-3. One of the primary challenges is the high production cost of boron nitride nanotube 3. Techniques such as arc discharge method and chemical vapor deposition require expensive precursor, extremely high temperature, and specialized equipment, which limits large scale production. And other significant and specialized equipment issue is post synthesis purification, as boron nitride nanotubes often contain residual catalyst, atmosphere boron, and other impurities that must be carefully removed to achieve high quality material. Achieving uniform morphology, consistent diameter, and precise wall number across large batches is also difficult, which restricts industrial feasibility. Furthermore, while covalent and non-covalent functionalization enhances solubility and catalytic activity, optimizing these strategies without compromising intrinsic boron nitride nanotube 3 properties remains challenging. From a biomedical perspective, comprehensive understanding of boron nitride nanotube interaction with biological systems, including cytotoxicity, biodegradability, and immune response, is still in early. Thus, BNNT-3 is not just a nanomaterial but a platform for innovation, sustainability, and advanced technological solutions. Now, I will discuss about the abstract. Boron nitride nanotubes are nanomaterials that structurally analogous to carbon nanotube, consisting of alternating boron and nitrogen atoms arranged in hexagonal lattice and rolled into seamless cylindrical tubes. Despite this similarity, BNNT-3 exhibit markedly superior thermal stability, chemical inertness, oxidation resistance, and electrical insulation properties. Unlike carbon nanotubes, whose electronic behavior strongly depends upon chirality and diameter, boron nitride nanotube possesses a wide band gap of approximately 5.5 to 6 electron volt. that is largely independent of tube structure. Over time, advances in chemical vapor deposition and catalyst-assisted growth techniques enable improved control over nanotube morphology, purity, and wall number. In this context, the term BNNT-3 is not standardized designation in the broader literature but is commonly used in specific studies or academic work to describe the particular boron nitride nanotube system, most often referring to multi-walled or three-walled boron nitride nanotubes or a specially prepared batch with controlled structure feature. Thus, BNNT3 should be understood as a subclass within the broader BNNT family, rather fundamentally different material. In recent years, research emphasis has shifted from pristine BNNTs towards functionalized and hybrid systems, where surface modification is employed to expand their applicability. BNNT3 type systems are particularly suitable for such modification because their multi-wall structure often enhanced mechanical robustness and larger surface area for interaction. Metal decorated hybrids such as palladium loaded BNNT3 materials have attracted significant attention due to their improved photocatalytic activity, absorption capacity, and environmental remediation potential. These hybrid structures combine the exceptional stability of boron nitride nanotube 3 system with the catalytic functionality of metals, enabling application in pollutant degradation, hydrogen sensing, and sustainable catalytic process. Overall, BNNT3 represents an advanced and application-oriented evolution of boron nitride nanotubes, reflecting broader transition of boron nitride nanotube research from fundamental synthesis into multifunctional real-world technology. Here, my presentation is completed, and thank you so much.